So let's talk a little bit about atomic mass. We briefly mentioned this when we talked about protons, neutrons, and electrons, and how much they weigh in the atomic mass unit. So again, this is a unit that we kind of made up, and it's based on carbon. So we said carbon-12. If we had isotopically pure carbon-12, carbon-12 would have, if you look on the periodic table, carbon has 6 protons, and it has 6 electrons, it has 6 neutrons if it's carbon-12, right? And so the neutrons and the protons are what make up the mass of the atom. And so if I have 6 plus 6, I have 12 particles that have any kind of mass to them, and each one has a mass of 1 atomic mass unit. And so that's where we get 12 atomic mass units for carbon-12. Okay, so we're basically basing everything off of carbon-12. All right, so here are the some other the mass of different isotopes of different elements. You can see hydrogen has two isotopes that are somewhat common. The first one has a mass of basically 1 atomic mass unit, and then this deuterium, this heavy hydrogen, sometimes it's called, has an extra neutron. And so if you look over here at the percentage, though, 99.9885% of hydrogen looks like, this hydrogen with 1 proton, or sorry, with 1 neutron. Sorry, not neutron, 1 proton. Only 1 proton. He doesn't even have a neutron. This hydrogen has a proton and a neutron, but only 0.0115% of it does. So what we want to do is we want to look at, if I just had a sample of hydrogen, what would the average mass look like? What would the average mass of the sample be? Since 99.9% of it kind of looks like this hydrogen, hydrogen 1, and only that much looks like hydrogen 2. When we calculate the average mass of it, it's going to look closer to 1 than to the other. The same thing happens with carbon. Here you can see there's 2 isotopes of carbon that are common. 98.9% of it looks like carbon-12, and then a little bit looks like carbon-13. And so I don't want to just say, when I'm trying to figure out what the average mass of my samples, I don't want to just say, okay, well, half of it looks like this, half of it looks like that, because it's not half. 98% of it looks like carbon-12, and only 1% looks like carbon-1. So I want to be able to systematically determine what the average mass of my sample would look like of all the isotopes. So I'm going to take an average of all the isotopes, and I need to know what their percent abundance would be. So these percents are percent abundance. So this is really saying, like, if I had 100 hydrogen atoms randomly just scooped up 100 atoms, 99.9% of them are going to look like, so 99.9 of them look like hydrogen 1, and the other little bit looks like hydrogen 2. All right, and so you can use something called a mass spectrometer to help you figure that out. We're not really going to talk about that right now. Mass spectrometer. So let's see. The atomic mass, I should have defined that for you. That's the average mass of all the atoms of an element as they occur in nature. So that's the average mass of all the atoms of an element as they occur in nature. All right, so let's try to calculate that. And so for chlorine, here they tell you there are 2 isotopes that are abundant in nature. So you have chlorine 35 and you have chlorine 37. This is the mass for chlorine 37. This is the mass for chlorine 35 in atomic mass units. And what you want to do is you want to figure out, using these percent abundance data, figure out what the average sample would look like. So again, 75% of it looks like chlorine 35, and only like 24.22% looks like chlorine 37. So we want to take a weighted average. So we want to weight these averages. So imagine, before we even do this, imagine you had a sample of ping pong balls and bowling balls. I think you're probably all familiar with that. Ping pong balls are really light, in case you're not, and bowling balls are a lot heavier. So suppose I had 75 bowling balls and 25 ping pong balls. I wanted to figure out what's the average mass of that whole sample. I can't just take the mass of a bowling ball, the mass of a ping pong ball, and add them up, divide by 2, and say that's my average mass, because that's not even close to what it's going to be. Only 25% of it looks like a ping pong ball, and 75% look like a bowling ball. So I would take something called a weighted average, and the way that works is I'm going to take this mass percent, so 75, so I have 75.78%, I'm going to divide that by 100, all right, and then I'm going to multiply that by the actual mass. And so that's just going to get rid of the percent sign, dividing it by 100. And now I'm going to multiply by 34.96885. And I'm going to add that to the rest of this. This is 24.22 divided by 100 times 36.9659. So you can work that out in your calculator. This is going to be my weighted average of all the isotopes. And when you work that out, you get like 35.45 atomic mass units. And if you look on the periodic table, atomic mass units, this is what it says on the bottom row there. That's the atomic mass of chlorine. So you can see that it looks more like chlorine 35 than it does chlorine 37, because 75.78% of it looks like chlorine 35. So when you take the average, it's going to be a lot closer to the one that's more abundant.